Welcome back, everyone, for one more amazing talk as part of the Trust Lab Curriculum series. So today we have Maciej, who's a research assistant professor at NUS. And prior to this, for 5 years, he was a research fellow and later a senior research fellow in the Devesh's group at NUS. And he did his postdoc before that from Aarhus and University of Warsaw. He also completed his PhD with Stefan Zamorsky. He has expertise in different areas of theoretical computer science, emphasis on cryptographic challenges, and particularly in leakage and tamper-resistant crypto. And he continues to understand how devices can be better secured in the face of real-world physical vulnerabilities. So today he's going to tell us about leakage models and particularly how to handle rejection. So happy to have you. Thanks for agreeing to do this, Maciej.
Thanks a lot. Thanks a lot for invitation and introduction. So yeah, I'll be talking about rejection and leakages, and it's a series of works with quite a few people. Gianluca, Antonio, Ananta, João, Lance, Mark, Maciej, Francois, and Daniela. It's a series of papers with different subsets of those authors. So let's start with the basics. Why do we leak? So there's a device, and device has some secret key. As we know, it's most secure when it's stored in the memory of the monitor. And it gets called from the memory to CPU, and it's like performing certain operations. The secret keys are used to encrypt, decrypt, etc. But the thing is that the computer is a physical entity and has physical properties, and those physical properties can be explored and exploited for the purpose of breaking the cryptosystem. And one of the first things that used to happen in this scenario was a timing attack. So maybe it's not so much, I mean, it is a physical property of the object that exists in a, there's time around us. And the idea was kind of like what I wrote in the abstract. So like hard computation takes longer, short computation takes shorter. So easy computation takes shorter time. And the idea was that we could create a specific series of messages or code words, give it to the device to decode or encode. And depending on like which of them were hard for it, so which of them took longer, which of them took shorter, we were getting some idea of like, oh, this computation is hard for this secret key, this is easy, so the secret key is probably in this range, and we would narrow this secret key with series of those observations. And eventually we would break the cryptosystem. And that was done for Diffie-Hellman, RSA, and a lot of crypto systems. And it's been done a very long time ago, like 30 years ago, we already knew about timing attacks. And ever since, we've been discovering more and more these physical properties that could be exploited. One of them is electromagnetic radiation. So the idea is that, well, the computer operates on bits, which is basically electrons running back and forth. The current is running here, the current is not running there. That creates certain signatures that have like electromagnetic signatures that can be observed. And what's more, it's like you get to like ridiculous scenarios where some static is gathering on the outside of the device. And there are papers that literally just measure the static charge that gathers on the device, observe it over time. The device is decoding, encoding emails. So there are like email clients that typically automatically decrypt the header of the email. So when you send the encrypted email, the header of the email gets decrypted automatically. So me as an attacker, I can craft certain emails with headers. I know this header will be decrypted, device is decrypting it, there's some static gathering, I'm observing this over time. And based on that, I'm breaking the device, breaking this cryptosystem. This is again quite a long time ago. There's a series of works that deal with it. Last one I've seen on the chart was a few years ago, not that long. I think like 5-7 years ago. It could break with like very small amount of leakage from the electromagnetic charge on the device, measured with literally a sausage. So to show how noisy the leakage can be, they literally touch the device with the sausage, and on the other end of the sausage there's a probe. So they literally just show this is possible with very stupid equipment. But that's not even the most ridiculous of the attacks. We will get to the most ridiculous in a second. There is also a very important class of attacks which talk about power analysis. There's different series of the simple power analysis, differential power analysis, a lot of that stuff. It all breaks down to the following. If you think of a cryptographic device like smart card or your credit card, it does not have source of electricity, right? It has to, like the chip on your credit card, it has to get electricity from somewhere. And if you observe the pattern of the electricity use, you can see that multiplication has different pattern than addition, and yet different pattern than like shift of the registers, so any kind of modulo operations. They all look differently. So we can see if, like, after how many operations, there was an overflow of the, if we're doing an RSA, we're over ZM. When was the operation of modulo M? Right, so we know how many operations we needed, and like, oh, we hit the wall, we had to reduce everything modulo M. We can see it with the power analysis. And that gives us like, oh, okay, so that means that the key has to be in a specific range. We observe it again, and like, oh, the key has to be in this range and in this range, and we get the intersection of those ranges, and they quickly converge to very small space of keys. So in the case of credit cards, the attack, I'm sure there are better attacks, but the attack I read about a long time ago was the credit card has 4-digit PIN. So it's 10 to the 4 possible pins. It will lock after 3 times, so it seems kind of secure-ish. But if you observe the power consumption of the credit card of like, signing few transactions, and it's not a huge amount of transactions, you can limit the space of pins from this to like 28 or something. So it's like, 28 pins, it's like that's not even 2 digits, right? So the security of the crypto system diminishes hugely just by observing the power. Moreover, it kind of doesn't matter if you're in secure enclave or not. It's both the manufacturer and the researchers know that SGX leaks. So Intel openly states don't use SGX as leakage proof enclave. It is not. It is leaking information. It's meant to leak information. There's nothing we can do about this. Don't assume any kind of security against side channel information. What the enclave is guaranteeing is that the computation will be done correctly and it will be signed and there's going to be a proof, but it does not guarantee that it will not leak, right? And we know it does leak. And one of my favorite crazy attacks is the acoustic attack on RSA. So what happens is the condensers and capacitors and all the other magical electronic devices that make the world run, when they discharge the electric charge, they kind of vibrate a little bit, and that causes noise, and it can be exploited. So there's a series of papers that exploit just noise the computer makes. And in the latest iteration, they just used microphone in iPhone. So it wasn't like very sophisticated spy level microphone that can, hear a mouse 300 kilometers from you. No. It was just a normal iPhone microphone that managed to break this system. Okay, so if now we know that we leak, the question is how do we leak? So the question is how to model it. It's kind of crucial because before we even start protecting from leakage, we have to know from what we are protecting exactly. So we need to have a mathematical model of all those things I mentioned. So how do we leak? There are a few models, they all look basically the same. There's gonna be a secret S on the device, and adversary will leak f of s, where f can be a non-deterministic function, and it's only a question what f is, what is allowed to be f. And here we have a little bit of gap between theory and practice. So what are theoretical models? The most popular one is bounded leakage model. So we say that this f, right? This f is bounded in a sense of the output is at most t bits, right? Apart from that, there's no restriction. It can be arbitrary function. It can be solving your NP-hard problems. Does not matter. The only restriction is it has t bits of output. And it's very popular model because it's very simple to prove things against this leakage. It's simple to build things that are, simple. There are overheads, but it's easy to make proofs with this kind of model. Another model that was gaining popularity is the idea was, hey, if I look at the power analysis, it's huge amounts of data, the whole power consumption graph. And it's maybe not conveying much information, but it's definitely not just t-bits. So motivated by this kind of approach was hey, let's consider mean entropy noisy leakages. And that basically says that mean entropy of the secret did not drop by too much. So this is the original mean entropy of the secret. This is the mean entropy of the secret after leakage. And we say that, hey, this leakage did not drop mean entropy. So this kind of conveys the idea of this leakage did not leak too much information about the secret. There is more models based on Rayleigh entropy, based on average relative error, based on relative error, stuff around that. They are all nice. I think this one is still the most convenient to work with. In particular, it sits in both of the models. But yeah, this is the theory part. Then there are gates of hell and practical models. And why the gates of hell? It will be kind of clear that those models are not very compatible between each other. One very popular, especially lately, model is statistical distance noisy, which basically says that if we look at the distribution of secret and the leakage, this is joint distribution. I'll be using this notation all through. So the dot means the joint distribution, cross means product distribution. So this says that if I observe the leakage from actual secret, and here I'm observing the marginals. So this is leakage from, I could write S prime if I wanted. I could write S prime to signify that this happens independent of this, right? That's a product distribution. And this model says that those two leakages are hard to distinguish. So it's kind of hard it's easy to confuse the leakage that came from actual secret versus leakage that happened to be from happen to happen kind of independently as a marginal distribution of the leakage. Here, the epsilon is not negligible. It's small but not negligible. Okay. Another model is mutual information model that says that S and f of S have some mutual information. Those two models are strongly connected by Pinsker inequalities, right? We know that they are connected. Finally, the third main practical model, and kind of most convenient from the point of view of theory, is the probing model. There are multiple variants of it: t-probing, random probing, average probing. The idea is as follows: we have a circuit, there are some wires, there are some gates, etc. Everything works nicely. And what the adversary is able to do, he has some probes, and he starts like attaching the probes to the wires, and he will be able to read the state on the wires, right? So he has some limited amount of probes. He can read the state of those probes. There are some models that capture the idea of like, hey, you can't really put the probe directly on a wire. What happens is you will get some kind of weighted Hamming weight of the wires nearby. It's all nice, and they're actually quite nice models, surprising. And we know compilers for the probing model. Okay, so it's time to ask ourselves, do we live in a simulation? And what I kind of mean by it is we live in a real world, and like there's a group of people who say that, hey, the secret is leaking and the leakage is function f. And also in a real world, there's another group of people say, no, it's not f, it's g. Right? So we have two camps, one says f, one says g, what can we do with it? And imagine we have s and we have this leakage that comes from function f, family f. If we could find a simulator, and the simulator does not see s, it only sees s via leakage g. So the simulator knows what function f he will try to simulate, but his only access to the secret is it can produce arbitrary function g from family g and obtain g of s. This is the only way the simulator can interact with a secret. He has one shot, produces one g, gets one output, and tries to do something with it. And the thing that he's trying to do is this. All right. What does it mean? It means that the simulator, using only leakage g, can produce something that looks like f. So if our device is resilient to leakage g, it will automatically be resilient to leakage f. Why? Because leakage f can be simulated with leakage g, and leakage g does not say anything about or does not leak too much information about the secret. Okay, so there's an idea of simulators, and those simulators will allow us to compare different leakage models. And we will be mostly interested in the simulator having access to bounded function g. So simulator will be able to compute, to create any g, send it. The only restriction is that g has only a few bits. So based on those few bits, he will be able to compute f. And that will mean that like our bounded security translates to any other security, or like whatever security model we will be able to create a simulator for. And this is important because we know a lot of constructions that are secure in bounded leakage models. So there was, we had this paper, Mother of All Leakages, in which we showed that all the popular theoretical models, so mean entropy noisy, uniform noisy, average dense, they can be simulated with bounded leakage. And moreover, they can be simulated in a very lossless way, which basically means that like I can move easily between the two models. So I know that this model can be simulated with t bits of leakage, and I know that those t bits of leakage sit in this model very tightly, so like I can move back and forth without much loss. This loss is really tiny. You'll see in a few minutes that is true. Sadly, the simulation is inefficient. So this simulator, first of all, runs in like exponential amount of time, and this G is arbitrary. It's only bounded leakage, but there's no like computational assumption, which means that our underlying primitive has to be information theoretic. Right? So if we could get rid of this inefficiency, we could work with bounded leakage that, first of all, not only bounded in a sense of number of bits, but also has to be efficiently computable function, and our simulator has to be efficient, so it's sufficient that we are some kind of computational security against computationally bounded leakage, which is like really nice, right? So if we could combat this inefficiency, we would be very happy. Okay. Moreover, what turns out in the matter of leakages is that those practical models can't be simulated. Like, it's not that we don't know how to do it, they can't be, there's impossibility. And I'll explain the impossibility in a second. The issue is that things don't really make sense, right? Just like the doors in Titanic. Imagine the following. So this is the definition. As I recall, imagine the secret has n bits, and our leakage with probability 1 over n will leak the first bit of a secret, and with remaining probability will output something uniform. Okay? What's this? What's the statistical distance between this and this? Well, if we're in this branch, we're outputting something uniform. So this is uniform independent of us. It looks the same. You can't distinguish in this branch, right? If we're in this branch, well, if we matched, we're probably slightly more likely to be here. If we mismatched, we know that we're here. So the distinguishing only happens in this branch, and like really only when there's a mismatch. So roughly this distance is around 1 over 2n or something like that. Think 1 over n, this range of parameters. Okay, this is reasonable leakage, everything's great. But now look at the following leakage. Again, now the leakage function will have n bits, not only 1 bit. With probability 1 over n, I leak the whole secret S. And with probability 1 minus 1 over n, again, I'll output some uniform string. What's the distance? Well, in this branch, again, I can't distinguish between uniform string and uniform string. And in this branch, okay, I'm pretty much like sure that there's a match, I'm here. If there's mismatch, I'm here, especially if the string is long enough. So what's this distance? It's roughly 1 over n. Okay, do you see the problem, right? We had a perfectly reasonable leakage before, and that had 1 over like roughly n, and now we have completely unreasonable leakage that leaks whole secret with inverse polynomial probability, and also gets 1 over n. So the issue is we call those events catastrophic events, like when the security of the crypto system breaks down immediately. And first of all, that's not what happens in real life. So what we observe in real life is like tons of measurements that like slowly narrow down the space of secrets. We observe power consumption, we kind of get a little bit of leakage, 500 iterations later, we infer some portion of the secret key. That's definitely not, we're never waiting for like one catastrophic event when the crypto system will just blurt out the whole secret key. That does not happen. And the other issue is that statistical distance can't distinguish between perfectly nice leakage and horrible catastrophic event. And that's the reason why we can't simulate. Because all the theoretical models clearly can distinguish between that, and they are very good at quantifying how much information is leaked in each round, how it accumulates, accumulate slowly, etc. And they definitely can distinguish catastrophic event from non-catastrophic event. And statistical distance or mutual information just does not scale well. The same happens for mutual information, right? With probability 1 over n, I get n bits of information. My mutual information is only 1 bit. The same as here, like my mutual information is 1 bit. So it's just, this is the issue of this measure. And
So,
okay, let's.
I have a question here. So should I ask?
Yeah.
Okay.
Go on.
So actually, one question here is that mutual information or just forgot the term, perceived information. These are kind of used as matrices in. I mean, when you try to measure the leakages and try to see how good they are, right? So in real world, they are being used. So does that mean, I mean, this result that you are showing here, does that mean that those matrices are not too good to use even when you are trying to do a leakage assessment?
I mean, they do give some indicative of things, but they certainly mean that it's impossible to, if you want to use those as a measure of some kind of how good the leakage is, it's gonna be impossible to get reduction between models.
Yeah, I see.
You will not get a full proper proof of security that follows from bounded leakage or something. You will have to work with this. And because they can't distinguish between those scenarios, it's kind of assumed, I guess, in practice that those scenarios don't happen, so we don't really worry about them. But it's very empirical, like.
Yes, in some sense. And another question is that, like, when you were describing the first case, right, when 1 bit leakage, it seems to me, I mean, somewhat close to what we do in random probing model, right? Like you assume that a bit is leaking with some probability and otherwise it's not at all leaking, it's just returning a bot. So does this result, this impossibility result somehow affects the, the usefulness of random probing security, also random probing?
No, because random probing has this inherent protection against catastrophic events that, where's my circuit? I don't know where's my circuit, but basically if you look at the circuit and you just tap few probes, you will just get few bits of information. They will be noisy, but they will only carry some small amount of information about the wires. And all those models of random probing, we assume that like either you had access to T wires in T probing, and average probing, we assume you got some kind of averages, noisy averages, but they all assume that, oh, I got some set of wires, I sum the values, and I get some noise. So this is the model.
I'm not talking about exactly this model. I'm talking about like the model that proposed by Jembowski, and I'm the bridge between noise leakage model and three threshold probing model, right? So that random.
So in their model, you have each wire leaks with some probability P.
Yeah, exactly.
Right. Yeah. So in general, you have that P fraction of the wires will be leaking. It's never gonna happen that all the wires will leak. It's just extremely unlikely that this sort of catastrophic event will happen.
So that is that failure event is this catastrophic event then in that model, right?
Yes.
Yeah. Okay.
In there, it's kind of so they define the catastrophic events as kind of, I don't remember which paper does it, but you've got the masking scheme of the failure.
Yeah, I think it's Sonia's paper on the first two the random expandability paper. They kind of give a explanation of the catastrophic event. I remember.
Yeah.
It's like all the wires are leaking with some that's a low probability for sure.
Yes, and that kind of bounds your amount of knowledge that you can get. That like this kind of scenario of like, oh, huge amounts of wires will leak, and that means that like I'll get all those inputs and I'll get all those inputs. That's just extremely unlikely.
Yeah,
because
this catastrophic event links with Yeah.
Yes.
Yeah. Yeah.
So the probing model is very nice in that sense. It can distinguish between these catastrophic events and non-catastrophic. Here, I'm predominantly talking about statistical distance and mutual information.
Yeah.
I guess they are nice to model things because they are nice to measure, but it's all empirical. Like, notice that, like, even if the system has some catastrophical behavior, but the catastrophic behavior is very low, and you all need the testing on some, 1,000 iterations, you will not see it. And there's there's a lot of model matching in between, and I would say it's an empirical model, and it will not work with our ideas of the proofs. That's my main concern with those. I'm not saying they are crap in a sense of don't use them in practice. I think they give us like there's theory models are hard to work with. They have high overheads. They have full proofs, but they have downsides, and like it's kind of depends what you want to do.
Yeah, I understand. Sure, please. Thank you for your explanation. Yeah.
Okay. So let's get to the simulator. So I will have a secret S. I'll get a output F, and I'll denote the leakage as Z. I'll make conditioning on S to make it clear that this depends on S. Okay. So my F will depend on S, and I want to simulate this with some bounded query. And the way it works is you take Z. This is not depending on S. So this is a marginal of the leakage. So this is Z taken kind of averaged over all possible secrets. And I sample T IID samples from this marginal Z. Again, this does not depend on S. Now, based on those T samples, I'll build G. So I'll hardwire those T samples into G. G will have full information of S. Its only restriction is that it can come back to me with only T bits. Right? And the idea is simple. I have Z, so I have a sample coming from Z, and I will just do rejection sampling. So I will accept ZI with probability roughly this. And what does it mean that I accept it? Well, I had Z that came in with this probability. That will kill itself with this, so I'll have a sample from this. So when conditioned on accepting, I know that ZI is distributed as ZS. That's the idea. If I don't accept, I reject, and I move to another one, right? I wait till I accept, and say I accepted some ZJ, and I know it's correct distribution. So if it's correct distribution, I just want to output here ZJ because it's from the correct distribution, right? So this will be correct distribution. So how do I output ZJ? Well, I could just write ZJ, but Z can be very long, right? Nobody prevents us from leakage being something stupid like sample a random Shakespeare sonnet and add 1 bit of leakage about X, right? It's going to be very little information and huge amounts of data, right? But like, notice that we want to just convey the information about ZJ outside, and outside our simulator knows all the Z's, right? So the simulator picked Z1 to ZT and hardwired them. I remember those Z's as a simulator. So all I have to do here is output J, so index. If I just output index, I can recreate which ZJ was accepted, and this is what? This is log T bits, right? Where if I had T samples, I'm just outputting the index that's log T bits. I lied a little bit here. So if I want to accept, this has to be a probability. So this has to be less or equal 1, which might not necessarily happen. So we need a scaling factor in a rejection sampling. And what does the scaling factor do? Well, it's just this max, right? And that corresponds to how many samples we need, because on average, we need like C samples to accept 1. So in general, we need around C samples, right? So this is important. This tells us how many samples we need, how much leakage we need, and how long the simulator will run. So everything is tied to this value. Log of this value will be amount of leakage. This value is the amount of samples and the running time. This is rejection sample, right? Now, there are issues with rejection, namely that this can be large. Like imagine this is large, but only in a very rare cases. Like there's like one case when this explodes and becomes huge. And in all the other cases, this is like perfectly nice and reasonable. And because of this small probability event, I suddenly have to have huge C, which impacts my number of samples, my running times, everything, right? So what can we do? We can cut ourselves a little bit of slack and allow some errors, right? So mind that like our simulator does not have to be perfect. It can have some small error, hopefully negligible. So what we can do is we don't really need this like C to be perfect maximum. We're happy with like reasonable maximum, whatever reasonable means. Think of like, yeah, again, if there's a negligible event where this ratio is huge, kind of ignore this event, throw this into error of the simulation and just play with the reasonable scenarios. Which also means that our acceptance probability has to change a little bit, because this can be greater than 1. Okay, then just like if it's greater than 1, then just accept it. Okay. This will create a little bit of error, but it's just really tiny amount of error. Okay, intermission, hockey stick. What's a hockey stick divergence? We call it SDT. This T is important between P and Q. It's a supremum over A and this entity. What it means is I'm looking for set A such that P of A is vastly greater than Q of A, is at least 2 to the T times greater than Q of A, right? It can be rewritten this way. It's sum over all x, max 0, P of x minus this. All right, how does it look on a picture? So imagine you've got P and you've got Q. So standard distance would be this plus this area, right? And SDT is we take Q, we multiply it by 2 to the T. It should be more like, okay, I'm horrible at drawing, but like you get the gist. This is our Q, this is 2 to the T times Q. And now I'm looking where P is not only greater than Q, but it's vastly greater than Q. So P has to be greater than this. So this is this area and this tiny area, right? Okay. I hope it's clear that the idea is I'm looking for a area where P is vastly greater than Q. Fun fact. So if we set if we set T to be 0, this is 0, this is 1. What is this? This is supremum over A, P of A minus this disappears, Q of A. That's just a simple statistical distance, P and Q. So this generalizes statistical distance. All right, fun fact 2. Imagine statistical distance T between P and Q is 0. What does it mean? That means that there's no area where this is 2 to the T times greater than this, right? So I can write this is 2 to the T. Okay, cool. Let's connect the dots, because that starts to look like something we've already seen. So when we look at our rejection sampling, we have this C that's reasonable. This is this ratio of P of ZS divided by P of marginal of Z. And now imagine that statistical distance T as dt, so hockey stick divergence T between ZS and Z is small. What does it mean? Well, that means that apart from this tiny error, this is not 2 to the t times greater than this. So this is not 2 to the t times greater than this. So this is mostly 2 to the t. There can be a little bit of area where it's error, but this happens. Okay, that's cool. That starts playing with our stuff. But we want our simulation to work for every S. So this only works for one. Now we want for every S. We have two options. We can ask for above to happen for every S. So we can demand that SDT ZSZ is small for every S. Or we can cut ourselves a little bit of slack and allow for a little bit of more errors and ask for almost all S. And that translates to this. If I look at this looks very similar to statistical distance zero, right? I have a joint distribution, I have a product distribution. And I claim that if this teeth hockey stick divergence is small, then something nice happens. Like reasonable maximum is 2 to the t for almost all S. Okay, how to incorporate this into rejection? So the theorem is as follows. If this is small, then we can simulate ZS using 2 to the t times log alpha samples from Z with error alpha to the minus 1 plus delta. This is delta, so this delta comes in as an error. This t is here. And why is this alpha showing up? Well, just simply because on average we need C samples, but we are quite likely to reject all C samples if we only run it once, so we have to run it multiple times. And this is this alpha, exactly running this multiple times, right? And for each of the runs, I need new safe Z's. So I just sample a longer string of Z's and I'll try to run it. So I have C samples. Okay, if I did not accept, I proceed to the next C samples. If I did not accept, to the next C samples, and I have whatever alpha of those. Okay, so if we play with alphas correctly, everything will work, and that's the only loss of our parameters.
So Maciej, once more. So alpha is the number of iterations, is it?
Yeah, think of number of iterations, yes. Okay. And the final theorem looks like this. If our hockey stick divergence is small, then ZS can be simulated using this many samples with this error. And this many samples, notice that this means how much leakage I need. I need t bits of leakage plus log alpha. And this log alpha is only losslessness of our construction. So we show that basically everything sits nicely in the classes. You can move between the classes in a lossless way as there's this log factor. That's the loss. That's the only loss. So if your system is resilient to t bits of bounded leakage, it's resilient to almost t bits of noisy leakage in like entropy setting. Okay. Okay, quick modification. Why are we sampling from Z? Well, the idea is that if I have a leakage, maybe sampling from the marginal distribution is the best idea. It doesn't have to be, right? We can sample from any Q. Maybe some Qs will be better, maybe some Qs will be worse. It will be clear soon what we want to do with it. But in general, we are not tied to sampling in our simulator from Z. We can sample from any distribution Q. And the definition of the leakage is as follows. The S is T delta GSD leakage from S. And GSD stands for generalized statistical distance. If there exists Q such that statistical distance between this joint distribution, here I dropped S, and I'll continue dropping S from now on. It will be clear when Z is correlated with S and when it's not. So this is joint distribution, this is a product distribution with our Q. So we will rejection sample from this to this, right? Yes, that's our definition. I'll explain why Q is important later. There's gonna be a nice example where Q kind of makes sense. Okay, composition. So imagine you have two leakages from S. You have leakage Z1 and you have leakage Z2. And you know that leakage Z1 is T delta SD, GSD, and Z2 is also T delta. Can we say something about those two leakages jointly? Right, that's one of the main tools that we need, because again, leakages happen in multiple rounds. There's accumulation of knowledge, and we would like to kind of control how much accumulation there is. Okay, so the question is, can we say something about this and this? Right, this is joint leakage of from the secret jointly from Z1 and Z2, and this is our S. And the answer is not quite for a stupid reason. The stupid reason is as follows. If you consider S Z1 to be S plus some uniform mask, and Z2 is the same uniform mask, and this U is completely independent of everything, then notice that Z1 on its own is 0,0 leakage. It leaks nothing, right? Because there's this uniform masks that hides everything. Z2 on its own is also 0,0 leakage. But Z1 and Z2 clearly break everything, right? So the issue is that here the internal randomness of Z1 and Z2 is correlated, but that's not quite what we see in practice. And I use quite because we kind of see some level of correlation, but it seems to be a weak correlation. But nobody really knows how to model it very well. And vast majority of the papers assume that if I see a leakage Z1 and I see a leakage Z2, it might be a random functions of S, but kind of we assume that the internal randomness of Z1 and internal randomness of Z2 are independent. And in that scenario, it is actually possible to get some kind of composition. I'll skip this proof. I'll just say it's a hybrid proof, like you replace Z1 with Q2, Z2 with Q2, and then you replace Z1 by Q1. And you can generalize this. And the general version is that if I have T1 delta 1 leakage and T2 delta 2 leakage, and Z1, Z2 are conditionally independent, so they are independent conditioned on S, so S is the only thing that correlates them, their internal randomness types are independent, then this jointly is just the sum of this. Nice and elegant.
So
We will.
Sorry to interrupt once again. So I have a small question here. So when you are assuming that the internal states are independent, but it's masking, right? You are talking about at this point. So in general, we assume this Z1 and Z2 coming from two shares are independent because you are using some randomness to generate them, isn't it? So why it is a more simplifying assumption and not a more practical assumption in your opinion?
So in general, the issue is that kind of what we get from probes is it seems that hitting one specific wire is kind of hard, and we get some interaction between the wires.
Oh, I see. So you are considering coupling and other physical effects if they are
Yeah,
there, right?
in practice they seem to appear, but at the same time we don't really know how to exploit them. I don't know of a single attack that actually exploits the correlation between the randomness. But also, like, look at the power consumption, right? It's a continuous line. It's if you observe some kind of leakages over AES, the power consumption between the rounds is correlated, and we don't know how to use that really, because there seems to be some kind of interaction between the leakages between the different rounds. But it seems to be there, and it would be nice to have some more generalized statements. And we do get slightly more generalized statements at the end, but it is slightly simplifying assumption. It's like nobody knows how to make use of it, so like let's just assume it's independent.
Yeah, so I mean, I can see like the physical effect, like as you said, like if there is some kind of coupling, it's more like a nonlinear effect. So that definitely makes the values being processed in the wires a bit correlated. But yeah, I mean, you are right in the fact that we really do not use the fact that two rounds are correlated, other than probably showing some negative results so far, I think. Yeah, so I got the point. So do you, okay, you'll come to the generalized result, I guess, right?
We will get to slightly generalized result at the end.
Okay, sure. Thank you.
So YQ, I talked about like, oh, we want this Q and we really want it. And the reason is kind of mathematical elegance. So think of S as there's one bit A and some string B. That's our secret. And now Z1 will just leak A. So what's SD1 of this and this, right? This is deterministic function of S. So this always matches the first bit. Here, Z1 is uniform independent, so it matches with probability half. With probability half, it doesn't match, but we have this one here. This one translates to double, right? This probability is never more than double of this probability, right? Because this will match with probability half. So this probability is always at most twice of this probability, which is captured by this one. So here we have distance 0. And similarly, if I define Z2 as A plus 1 if B is all 0, so Z2 is A if B is non-zero, and it's A plus 1 only if the whole string is 0. Okay? What's the statistical distance now? Well, again, this is 1-bit leakage. It's deterministic, and this is uniform bit. Again, it will match with probability half. Again, we have this 1, so this is 0. Okay. Now, let's quickly talk about what's the difference between S times joint distribution and S times product distribution. S product distribution. So S product joint, S product, right? So what's the difference between product of those two and joint distribution? Product is easier. Product is, well, this is uniform bit, this is uniform bits. It's two uniform independent bits. What's the joint distribution? Notice that, like, B in general is highly unlikely to be all 0. So almost always this is equal, right? So Z1, Z2 as a product is almost always same bit. It's one bit, but uniform, but it's the same bit on both positions. And it's two different bits with extremely small probability. Okay, let's evaluate this. This is again a deterministic function. These are two uniform bits, independent. So this is probability 1/4. It will match what it should. So this is at most 4 times greater. Great, that's captured here. Like 2 to the 2 is 4. It exactly captures this, so here we get 0. Cool. But what happens here? What if S lives in a scenario where B is indeed 0? This should be two different bits. But two different bits do not happen very often in this scenario, right? So this probability is 2 to the minus size of the B, smaller than this probability. So we would have to put here 2 to the size of the B to get 0. Okay? So it turns out, maybe counterintuitively, that sometimes taking a product of two distributions is better than looking at them jointly. And that leads to the following scenario that, like, if we define Z as T delta leakage, if instead of Q we have Z here, then to show that this, like, first of all, this can be simulated anyway. That's not a problem. But to show that this as a joint is a nice leakage, it has nice triangle inequality, we would have to show inequality between this and this, right? This is what this definition means. I look at the joint and the product. But the product here, that's a joint distribution, right? And this we just calculated, right? This behaves horribly. This behaves nicely, this behaves horribly. So that's why we throw in Q. So Q makes talking about it nice. Simulation works all the same, but it's nice to say that, like, joint leakage is just plus of the leakages. Okay, I'll skip this part. I'll just say that there's differential privacy, and differential privacy has this advanced composition, and it connects with GSD model, and we are able to get it. But the problem is that both in differential privacy and in our proof, the parameter T has to be super small for this advanced composition to work. So it's kind of, nice but useless. There is better way of composing, but it works in a specific range of parameters that's not very interesting for us. It might make sense for privacy amplification, but not for us. But I'll skip this part. Okay, why do we care? We care, first of all, because if F is bounded, then it's T0 GSD. We care because all those leakages fit nicely into GSD. And it's a generalization of SD noisy leakage, so the practical leakages should be sitting in it. And as we can do better with T, we get better signal to noise ratio and better behavior. If I swap the order of two things, so instead of joint product, I look at product and joint, then I can be simulated using probing, which means that if I have both inequalities, both hockey stick divergence with respect to, it's not symmetrical, right? So if I get it with respect to product joint and joint product, then I'll get that I can simulate both from probing and from bounded leakage, which is great because we have compilers for both in some sense. Okay, what really sucks is that GSD is hard to test, hard to calculate parameters, even with model matching. Outside of very specific, like Gaussians, if the noises stop being Gaussians, it becomes really annoying. And also simulator is inefficient, which means that the underlying scheme has to be secure against unbounded adversary, which is slightly limiting. So let's fix it. First of all, let's take Q that's uniform. Okay, what does this mean? Well, this means that the reasonable maximum of this for a reasonable maximum is at most 2 to the T for almost all S's. Okay? What would happen if I had max instead of reasonable max? If I just had max of this? Well, that means that ZS has just high entropy. Okay, great, easy to check, easy to work with. But we have reasonable max. What does reasonable max mean? It just means smooth entropy. Okay, cool. That's still easy to work with our models. It's easy to check, especially with model matching. And the advantage, it also works over R. So if you look at like power consumption or electromagnetic radiation, whatever, it's usually real numbers, not bits. Okay, so if we're talking about real numbers, I have to introduce Lipschitz functions. So I'll say f is L Lipschitz if f does not grow faster than from x to y does not grow faster than the distance between x and y times the constant L. This is the constant, right? So yeah, the growth of the function from x to y cannot be greater than this distance times L. So it cannot grow faster than like linear function with coefficients L, and it cannot drop faster than the linear function with coefficient minus L. So our function is always sitting in this nice cone. Now, if Z is Lipschitz, and it's mostly tight, what I mean is that ZS sits in some nice domain. This D can be even large, but like in general, that's what we see. This does not escape to infinity. There's issues with infinity, so we don't really want to work with infinity. We assume the bounded domain with very high probability for most S. Then what happens? Notice that you have your ZS, you have your uniform distribution, whatever, and I claim that because ZS is Lipschitz, it cannot grow too fast. Okay? If it cannot grow too fast, then its ratio to the uniform distribution should not be too big, and we will exploit that. So to be very specific, one can calculate that like the fastest Z can grow is if on the interval of size R, it will grow as fast as R times L, but ZS has to be a probability distribution, so we can calculate that this distance is roughly square root L. If this distance is square root L, that gives us, that bounds this divided by this. So it gives us the ratio of this to this is not horrible. Okay? So what can we do with our simulator? First of all, we replace Q by uniform. And it's great because now we can calculate parameters easily, but it still requires 2 to the t samples, and it's only efficient if t is roughly logarithmic. So I can't have too many samples. And there's a way of dealing with it. So the question is, can we do better? Can we find a better distribution than uniform that still allows us to calculate parameters nicely, but also allows us to be efficient? And the question is basically how to make rejection sampling efficient. And the picture is as follows. Where's the inefficiency? So I have my Z, I have my U, and the inefficiency comes that there's a small area where Z is vastly greater than U. So if only U could be closer to Z here, but U has to be a distribution, that's cool, I can sacrifice this bit, right? Here U is useless, right? I'm sampling this area and I don't really need to because I'm very rarely here. So I could lower this and increase this, and that would make it great. But there is a problem, right? Because my ZS, depending on S, can look differently. So for S1 can look like this, and I would like to be something like this. But for S2, I would like to look like this, right? So suddenly I have a problem of how to match U. So the best efficiency we would get is of our distribution Q hugs Z. But that means that Q has to depend on S, and that's a kind of problem. And a problem because when we look at the simulator, we first have to sample from QS. And that's only gonna happen if like I can do it. So like wait, but like I want it to depend on S. So this is kind of a mismatch, and I can't really sample if I don't know S. If I could sample, then it would not depend on S. We're starting to chase our own tail. But what if I told you that we kind of actually can do it? So what I'll go after is this Q. So it's basically Riemann integral approximation of Z. Now it should be clear why I picked Lipschitz functions, because Lipschitz functions really like to be integrated and approximated this way. Okay. So how to sample from QS? So in this scenario, I will try to hack ZS1. In this scenario, I'll try to hack ZS2. So I really depend on S. So how to sample QS without knowing S? Well, you can't, but you can cheat. So how to cheat? Simulator will pick a small d, will pick samples from a uniform IID samples from an interval 0d. And now they will pass it to G. What G will do is, first of all, we'll cut the domain into small pieces the size d. And then it's gonna approximate our ZS with standard Riemann style approximation. And second thing, how do I do this approximation actually? I will pick J proportional to the mass of the interval. So I'll pick J equal 2 proportional to the size of this. I'll pick G equal 0 proportional to this. I pick J equal 50 proportional to this, right? So I pick proportional to this. And now I claim that if you pick J as follows, your Zi plus J times D is distributed according to QS. So think of green stuff as QS. Now I created a sample from QS, right? Now I can accept with, okay, there's again gonna be the C that I disregard. I will accept with probability proportional to this. And if I reject, I have to loop back and I have to select new interval. Like looping back here does not work. So you have to go back, select a new interval, create a new sample. So you discard Zi, you move to Zi plus 1, you select a new sample, new interval, you create this sample. Eventually you accept. And now what do you have to output? Well, you have to output this index. And the only thing for me to recreate this sample is, hey, this index and this J. Right, so all I have to output is I and J. And now the comparison. So if I just use standard U, I will get square root L running time, which is number of samples. Log of this will be the amount of bits that are leaked. And that's great as long as my Lipschitz is small. If my Lipschitz is large, then I can use this trick that I just described above. I can set D to be very small, that offsets the leakage. And cool, I get my small running time, small number of samples. And it all happens at the cost of a little bit of extra leakage. This is basically number of intervals, right? So I have to give you the interval. There's capital D divided by the intervals, log of this extra bits. Which is like, notice that even if this is exponential and this is exponential, there's going to be a polynomial small number of samples, right? If this is 2 to the square root n, that's going to be square root n extra bits. Cool, okay? So this gives us a way of trading a little bit of extra leakage for vastly improved efficiency of the simulator. And now a simulator is running in this time, is needing log of this number of bits plus this. So in general, it's running on a very small number of bits. It's running potentially on like logarithmic number of samples, which is great, efficient. And our underlying protocol can be computational, right? So that's great. And as a last kind of remark, semi-joke, if you think of the world, there's plenty of background cosmic radiation, like neutrinos hitting us and stuff. So what usually happens is you've got your X and you have your measuring device, and what happens is there comes a noise N, right? There's some kind of noise introduced by the measuring device. And this extra noise, if X is bounded, it acts as a smoothing factor, right? So it will, because the noise is usually Gaussian, it will add a smoothing parameter. So it will create a Lipschitz function, and that basically means that if your device is noisy, you can't get too many bits of leakage. I also promised a little bit of what happens with correlated samples. So this idea, literally 30 more seconds. So this idea can be generalized to higher dimensions. So you don't have to live in one dimension. You can think of okay, we approximate using horrible at drawing. I think I managed to get some kind of paradox here. But you can split it into not intervals, but squares and 3 dimensions cubes and so on. And really all you care is that this is Lipschitz and you want to control the Lipschitz factor of this. So if you have multidimensional secret vector S and some multidimensional noise, even if this noise has correlated coordinates, right? We can deal with it because we can calculate this for a variety of noises. So the standard model would be I have some vector of secrets and I leak some small bounded information about this vector, which by itself is also some kind of vector. And there's a noisy Gaussian with some covariance matrix C. So there's some N0C. And based on this covariance matrix, we can calculate Lipschitz coefficients, Lipschitz factors, or just correct. You don't even need Lipschitz. All you care is the correct maxima over the intervals. So there's a lot of optimization you can do. If you have a very nice model, you don't even need to look at Lipschitz. You can look at something that gives you better calculations. But in general, what we are able to do is deal even with, because of the shift into higher dimension, we can deal with some level of correlation between the noises. So yes, if the leakage is multidimensional with Gaussian, even if this Gaussian is not canonical, we can deal with it and we can simulate it nicely. Yep, that will be all. Sorry for running 10 minutes over time.
Thank you. Yeah, it was great. I think this is pretty nice that finally all these different leakage models are kind of falling into the same. I mean, otherwise it's been a little bit messy, I guess, tying this bridge between. So Shaindeep was asking you a question. He actually works on side channel. So I think that's why for him, several of these probing models and stuff.
So I think from our point of view, probing model and bounded model are very nice and reasonable. The statistical distance by itself has its drawbacks, and it will be hard to incorporate any kind of proofs into that. That's my takeaway. But yeah, I think it's kind of cool to connect those models, and also I really like this cosmic background radiation. I mean, it's semi-joke, semi-true, but if your device is very noisy, you will not be getting much leakage. That does not stop you from accumulating the leakage over time. So
Right.
if you have multiple rounds, you obviously can accumulate it. We showed the composition theorem for that.
Right.
But I mean, that's in some extent unavoidable, right?
Right. Makes sense. Yeah, thanks again. I think Chetan and Shandy said thank you for the talk. They just left like a couple of towards the very end, actually. Yeah.
I forgive them.
Thanks.
All right, thank you. Thanks a lot
Thank
for
you.
having
Thanks
me.
so much. Yeah. Thank you so much. Yeah, this was a great talk. Thank you.
Bye-bye. Thank you.
Bye.